Hello everyone. Today we're going to be talking about power and efficiency. Power and efficiency. And this should be a nice follow-up to last lesson. Hopefully we will have spent a little bit more time in class talking about energy by then. But power is slightly different. It's related to energy, but it's not exactly the same thing. Now you would have heard power being used in different circumstances, especially when we're just having conversations. It's used in terms of describing the strength of something or how quickly it moves. But in physics, power is defined as the rate of change of work over a given amount of time. So here I've got power equals to the change, a change in work done or a change in energy divided by some time interval. The units of power is the watt. Okay, is the watt. I'm not asking you a question here. It's named after somebody. Is the watt here. So that's the units of power. And that, of course, is equivalent to joules per second, right? Joules itself is a derived unit, and watt is also a derived unit still. So that's the definition of power. Okay, the power is change in energy over time, the rate at which work is being performed over some given interval. Now, there's another equation as well for power. There's actually multiple equations, depending on which context or which topic you're looking at. But this one is the key. The other equation I want to relate power to is the following. I want you to recall from last time, I'll do a little aside here, that work is F times some change in, so I wrote it as Fs last time. I'm going to write that a little suggestively as some change in position, right? So some force times some change in position. Okay. Now, if I replace the W in this equation with this, then we'll find an alternative form for power. So I could write this as F, oops, the pen has stopped working for some reason. There we go. F delta X over delta T. And you'll notice that this may seem familiar. Delta X over delta T, that's change in position over time. Well, that's just your average velocity. Okay, so power could also be represented as force times the velocity. And I've written average velocity here, but if you make this time interval short enough, you can actually consider v to be the instantaneous speed or the instantaneous velocity of the object here. Okay, let's apply this in a given context. So let's do a simple problem where we have a car like this, and it's traveling at, let's say it has a mass, my pen has stopped working again. This is a good start. The car has a mass of, let's say, 1,200 kilograms, 1,200 kilograms. It's traveling at 10 meters per second. Let's make it 10.0, so we have at least two sig figs between the two of those values. And it speeds up, and in about, it speeds up to a velocity of 20 meters per second. And the time taken for this to happen, let's pretend is, I don't know, 1.1 seconds. So it takes 1 second. Oh, maybe let's be a bit more realistic. Maybe 2.1 seconds. Doesn't really matter. So we have a car on the left. It's traveling at 10 meters per second. It takes 2.1 seconds to accelerate to 20 meters per second. And the question is, what is? Or maybe a better question is, what minimum power is needed for this to occur? Okay, that is the question we're going to answer. Now, last lesson we were introduced to kinetic energy, and this is going to be handy because if we want to apply power, which is going to be a change in work done or a change in energy over time, well, we're going to need to calculate the change in energy, right, as our numerator. So we'll have to figure out the energy before and after and divide that by the time taken. So the energy after the acceleration is 1/2 times 1,200 times 20 squared. That's the kinetic energy of the car after it's accelerated. Subtracted from that is 1/2 times 1200 times 10 squared. That is the change in energy divided by 2.1. 2.1, and I got roughly, to two significant figures, 86,000 watts. So approximately that. So that's equal to 86 kilowatts. Okay, there you go. Let's do one more example, and then we'll introduce perhaps one or two more examples, and then we'll introduce efficiency. Here's another one. We have a block of 50 kgs, and we want to lift it now over a height of 12 meters. And let's say it takes 0.50 seconds for this to occur. Now, the problem with this is it's not easy to see how we're going to use kinetic energy here. Right? It was easy to see in the previous version because we had the velocities. But remember, the power doesn't really care whether you use kinetic energy or not. It wants to know the change in energy, full stop, the end. Now, when something is lifted up into the air, it's given, I should be more precise, when it's moved away from a center of mass, a gravitating object, it means it will also possess some gravitational potential energy. Now, that last lesson or last video was given by mgh, or mg delta h. That is the change in gravitational potential energy. It's going to be 50 times 9.8 times the change in height, which is 12, over 0.5. And that'll be your answer there. I'm not going to work through the calculator work there. You can chuck that in. It's fairly straightforward. Let's insert a new page now. Let's insert a new page. Okay. What I'm now going to introduce is efficiency. This can maybe be a subheading for you. Now, there's a couple of ways that you can define efficiency. First of all, its symbol is sometimes written like this, the Greek symbol eta, right? E for efficiency. And it could be defined as one of the following. It could be defined as useful energy out over actual energy in. So the energy you get out versus the energy you put in. Or you could define it as the useful power output over the actual power input. So if a question has got a lot of quantities to do with energy in it, you could use the left version. Or if it quotes a lot to do with power, then the right version would be easier. But they are equivalent. In fact, they're directly equivalent because you can imagine if you divide it by time on both sides, you just get to that version, right? Okay, so let's do a question to do with this. Let's do a question to do with this. And let's say, for example, we have a, I'm just getting some inspiration here. We have a motor car, so just like a toy car or something. And let's say it has a mass of 1.0 kgs. Okay, it's a small toy car, and has a constant velocity of, I don't know, 0.1 meters per second, 0.10 meters per second. And what else should I tell you? I'm also going to say that the motor in here, in this car, the power of that motor is approximately 3 watts. Okay, approximately 3 watts. Now, at the same time as that happening, there is also a frictional force pulling back onto the car. And there's a frictional force of, let's say 6.0 newtons pulling back on the car. All right, we're set up now. Thanks for bearing with me as I flung those numbers together. Now, the question I want to ask is, what is the efficiency of the motor? What is the efficiency of the motor? Well, let's start calculating it. So efficiency, remember, we're giving powers here. We're giving forces and velocities, and that was also related to power earlier. So it might be in our best interest to think about the power out versus the power in. Okay, the power in. Now, the power input is the easy part. We're told that the motor has an input power of 3 watts, so that's going down the bottom in there. The power output's a little tricky. But we know that the power output can be considered as a change in energy over change in time, or it could be considered as force times velocity. And in this case, we are given a frictional force and a velocity. Now, some of you might be thinking, well, hang on a second. We can't just do 6 times 0.1. We can't do that. Well, let's think about why we actually can. In this case, the velocity is constant, which means the pulling force or the forward thrust force of the car, the driving force, is probably a better way to say it, the driving force on the car has to be equal and opposite to the frictional force to allow this velocity to be a constant 0.1. So it's not so much that I'm picking 6 because it's the frictional force. I'm picking 6 because the driving force must be 6 because it's traveling at a constant velocity. So the power output must be 6 times 0.1 divided by 3. I'm sure I could do this in my head. It'll be like 0.2 or something, but let's just be extra sure. So there it is, 0.2. That means that the motor has a 20% efficiency. 20% of its power is being converted into something useful. And there you have it. There's a little quick lesson on power and efficiency. I hope you understood that, and I'll be assigning some questions to my class later, but if you're just viewing on YouTube, I'm sure you can find your own. Anyways, take care, folks, and thank you very much for listening. Bye-bye.